Okay. So this is the name of this course was Elementary Set Theory. The Elementary Set Theory is a course taught at the first year, at the entrance to the university. So I thought it would be a first year course. So I designed the syllabus, easy one, too easy. Then I learned that this course was a third year course for third year students. Then I changed my plan. The course will be more advanced. Actually, it will not be elementary at all, not even intermediate, but it will not be difficult. It will be deep. It will raise some philosophical questions even. Unfortunately, there will not be too many exercises in this course. I cannot give too many exercises. And the books. What was the subject first? What should I talk about? First, I will talk about orders. Mainly well-orderings. This will be the first chapter. The second chapter will be about ordinals. These are special well-ordered sets. And then cardinals. These are special ordinals. We may think of ordinals and cardinals like infinite numbers, kind of numbers, finite or infinite. You will see that there will be different kinds of infinities. There will be small infinities, large infinities, even larger infinities, and we will try to classify, but fail, infinities. And doing this, we will need very special axioms. The other axioms of set theory, the easy ones, will be given in the other course. It's yesterday. It was on Tuesdays. Tuesdays. I forgot the time now, but it must be announced. This will be easier axioms. Here there will be much more special axioms. Special and dangerous. And dangerous. What do I mean by dangerous? I mean that it is well possible that from these axioms, a contradiction in math arises. It's very possible. Unlikely, very unlikely to my belief, but it's possible. We will state very special axioms like axiom of displacement. And axiom of choice. Only two, actually. Only two axioms. I don't think I need another axiom. And of course, from axiom of choice, Zone's lemma, which is a consequence of it. Okay. And we will do some arithmetic with ordinals. There are addition, so with infinite numbers. We will define addition and multiplication. of ordinals. And cardinals. It's called ordinal arithmetic. And it's called cardinal arithmetic. Cardinal arithmetic will be trivial. But it will take time to show that it's trivial. Some time and effort to show that it's trivial. And to define ordinals, I will follow von Neumann's ideas, methods. Probably also cardinals. This method is probably due to von Neumann, but I'm not sure. Okay, let's start with one, orders, and then I will not insist on orders. I will concentrate on well orderings. One, orders and well orderings. 1.1 say orders first of all. Orders. What's an order? A partially ordered set kısmi sıralı in Turkish. Kısmi sıralı küme. A partially ordered set structure, or a partially ordered set is a set together with a binary relation often denoted less than or equal to. So a binary relation, it means that you need two elements for this to make sense. X is less than or equal to Y, such that satisfying O1, X is less than or equal to X. Well, there are two ways of defining orders, like this or like that. This is strict inequality. This is, in a larger sense, inequality. I don't know which one I will take. This one probably, but I can also do with this one. One can do with both. I will take this one. So if you have this, then X will not be less than X. Will not be. X less than or equal to X. O2, if X is less than or equal to Y and Y is less than or equal to X, then X equal to Y. O3, if X is less than or equal to Y and Y is less than or equal to X, Z, then X is less than or equal to Z. This is called transitivity. And this is called anti-symmetry, I believe. This is called reflexivity. This is not important, of course. The names are not important, but transitivity is important. Transitivity. This is very useful. If instead of this I took this, then the axioms will be the following: O prime 1, let's say, x is not less than x. This is false for any x, of course. This is also for any x, for any y, for any z. O2, O prime 2, less. If x is less than y and y is less than z, then x is less than z. Oh, sorry, yeah, O prime 3. Yes, that's it. Only two axioms here, if I'm not mistaken. You see, we can pass from here to here and from here to here very open. If you have this, if x is less than or equal to y, if you have this, then you can define x less than y by saying x is less than or equal to y and x is different from y. You can define this way. And if you have this here, then you can define x is less than or equal to y if and only if x is less than y and x equal to y. Very often, if you go, well, there are some instances where these definitions are not very equivalent, I believe. I forgot now, but very often they will be equivalent. Either you take this or that, you will get the same results. You will be able to pass from one to the other easily, like this. This is called the partial ordering. Okay, so you can, if you want to, you can say, you can write the small elements at the bottom, the larger ones on top, like this. For example, like this. This is A, this is B, this is C. This means that A less than B, A less than C, B less than C, B less than D, and so on. If it's finite, of course, you can do like this. If it's infinite, you can view an ordered set like a picture like this. Small elements here, large elements on top, and you can join them like this to show that this is small, this is large. This is just a representation. It has a name, actually, but I forgot the name also. Let me give examples of partial orders. Examples. You can take x to be is a set x, let's say, a set x. You can take x to be z with the natural order. Five is less than 7, for example. This is the order, and this is actually a total order. These may not be total. You may have, for example, here, these two elements are not comparable. One is not less than or equal than the other one. You may have elements which are not comparable. If you want the total order means total order for x, y, either x is less than or equal to y, or y is less than or equal to x. And in this case, either x is less than y, or x is equal to y, or y is less than x. This means that let's call this TO, total order. It means that you can compare any two elements. Here also, you can compare any two elements. Either one is less, or the other one is less, or they are equal. This is the total order, of course. Example. Second example, take again x equal to z if you want to, or natural numbers, this is numbers, with define x is less than or equal to y, if and only if x divides y. We define this, let's say it like this. Listen. You see, sometimes if there are several orderings, you can note the orderings like this, or like that, or like that, or like that, or like that, you know. Or sometimes like that. There are different notations for the orderings, for the binary relation, x less than or equal to y. Is this understandable? Kaç öğrenci var? How many students are there?
38 kişi var.
Okay, people, do you understand? Is it easy? Is it difficult?
Yes, sir. Normal, actually.
Normal, okay. So, what about the other 37 students?
I agree with Tekin.
Hmm?
I agree with Tekin actually.
Okay, okay. Okay, please stop me when something ununderstandable comes. So, for example, here, 3 is less than or equal to 6. 3 is less than or equal to 9. But 6 and 9 are not comparable. Actually, with Z, this will be false. With Z, it will be false because 5 is less than or equal to minus 5, because 5 divides minus 5, and minus 5 is less than or equal to 5. But if it's an order, we are supposed to have 5 equal to minus 5. So with Z, this will not work. But 6 and 9 are not comparable because neither 6 divides 9 nor 9 divides 6 are not comparable. We can't compare them. What else? Example. Let's take any set and X subsets of A, parts of A, the set of subsets of A. And the ordering, take any subset here, let's say B and C. B will be less than or equal to C if and only, this is definition. B is a subset of C. Then this is also a partial order. The set X has the smallest element A, has the largest element, empty set. Largest element A is the largest subset. And if B and C are here, there's a largest set which is less than B and less than C. B intersection C is less than B, of course, is less than C also. And of course, it is greater than any element which is less than B and less than C. If you have something which is a subset of B and C, it must be a subset of B intersection C, of course. And among the elements which are larger than B and C, you have B union C. This is the B union C is larger than B, larger than C, and it's the smallest element which is larger than both B and C. It's called a lattice. Such a thing is called lattice. What else? Example, if X is a partially ordered set, and Y is a subset of X, then Y is also, Y can be, let's say, then Y can be partially ordered by the order of X, by the partial order of X. You have a partial ordered set, X, you have a subset Y. Well, there's order also, the same thing, right? You say A is less than or equal to B, terms of Y. A is less than or equal to B if and only if A less than or equal to B in X. What else can we say? Well, what we can do is this, for example, let x and y be two partial orders. Assume they are disjoint. Assume they are disjoint. If they are not, there's a way of making two sets disjoint. Do you know this? If x and y are two sets, which are, let's say, disjoint, if you place x by x Cartesian product 0, now the elements of these are x comma zeros. If x is here, x comma 0 here, and y by y times 1, the elements of these are of the form y comma 1 for y in here. Now these sets are disjoint. Because last coordinate here is 0, last coordinate here is 1. Right? So this is a trick to make two sets disjoint. And now x is partially ordered. Of course, you can transfer this order to here. You just forget about the second coordinate. And also you can transfer the order of y to this set, because there's no difference between this set and this set in set theoretical. You know, they are the same sets. And now, okay, so do the following. Let's say put y on at the top, put x on top. Okay. If two elements here, just take the order of y. If a and b are here. If a is less than or equal to b, then in y, then say that a is less than or equal to b in this union. If they are both here, c and d, you also take the order of x. If one is here, e, and another one is here, let's say y, and here x, then say that this x is always larger than y. So everything in x is larger than y. So you can say, okay, so define a new order. Sometimes I would say just order instead of partial order. A new order on x union y, this disjoint, by. So you take two elements here, let's say a and b. A is less than or equal to b, if and only if. A is less than or equal to b in x, if both a and b are in x. A is less than or equal to b in y, if both a and b are in y. A is less than or equal to b if a is in y and b is in x. Then this is a partial order. You keep the same orderings in y, the same ordering in x, and then you proclaim that the elements of x are larger than the elements of y. But there are several, for a special instance, you can take natural numbers, 0, 1, 2, 3, 4, so on. And you can add 1 point here. This is a special instance. This is my y. This is y. The natural ordering on natural numbers. And this is a singleton set. Singleton set is always a partial order. So, and then what you can do, you can put this to the beginning and the other ones to the end. There's one here, y here, and x here. This will be 0, 1, 2, 3, 4, and so on. And this will be here. You can call this -1 if you want to. There's no difference between this and y. This and y are isomorphic. Just send, put y here again. 0, 1, 2, 3. Just send -1 to 0, 0 to 1, 1 to 2, as you see, send x here, a y here, to y plus 1. Then you will get an isomorphism. In other words, there's an order preserving bijection between this sum and this kind of sum. I'm summing two orders. But this is different than this one. This has no last element, because y has no last element, but this is the last element. So they are not isomorphic. They are the same. They are different orderings. This ordering is important in math. It will not be important for us, but in math it's important. Maybe let us think about this ordering. So I take x equal to n, and I say that x is equal to y if and only if x divides y. Maybe I should take, let's take off 0. Let's take off 0. Okay. So this has a smallest element. One is the smallest element, because 1 divides all numbers. And then on top of it, you have primes. 2, 3, 5, 7, 11, and so on, infinite many, of course. And then on top of this, we have 4. 4 is here. And 6 is here. 6 is larger than both 2 and 3. 15 is here. 10 is here. Here we have 30. Right, 30. And above we have 60. And 60 is of course larger than 50. And I have 15 here, not 15. I don't have 15 here. I must have 15 somewhere. 15 is here. 15 divides 30. So this is okay, it has no end. It's a huge, it's uncountable, it's true, but the relationship is very complicated. Here I have 77. I have 121, 49, and so on. None of these are total orders except the first example, natural numbers, integers with the natural ordering. Okay? You can speak up, you know? If you have only one, if you have a singleton, A, say, there's only one way to order this. There's nothing to be done. Yeah? Then A is less than or equal to A. That's it. Right? There's nothing else. If you have two, then you have three different ways. You can say A less than or equal to B. You can say B less than or equal to A. And you can say nothing. Just don't order A and don't compare A and B. No relation. These are, of course, isomorphic. We will see isomorphism later on, but we understand. Who cares that A is less than or equal to B or B is less than or equal to A? Right? Send A to B, B to A. It will preserve the ordering. If you have three, then you have more complicated. You have three elements, three distinct elements. You can have A less than or equal to B less than or equal to C. Here we have three factorial ways of total orders. You decide which one is first. And then three factorial of them, of those. You can just compare A and B, and you don't say anything about C. Of these, we have 3 choose 2. You choose 2 elements, but then you can make A less than or equal to B or B less than or equal to A times 2. So it's 12 of them. And then what else? And then you can say nothing. No relation. That's it, I believe. One of them. So you have six of them. 6 and 6, 12. 13 different orders, partial orders on this. But well ordering only 3 factorial. And of course, these are all isomorphic to each other. These are all isomorphic to each other. There's only one here. So you have 3 isomorphism types. Yes. You can have A less than equal to B and A less than equal to C. Right. So you don't compare B and C. Of these, I have 3 of them. You just select the smallest element. So these are of this kind, A, B, C. This is of this kind. Don't compare this. And this is of this type. Nothing can be done. And this is A, B, C. This is this. This is this. So you have 6, 12, 13, 16 of them. Okay. And next, I should define homomorphisms of, there's something that we can do is this also. So if, another example, if X is less than or equal to is a partial order, we can just reverse the order. Define, let's do like this, via X is less than or equal to, in this sense, than Y, if and only if Y is less than or equal to X. You reverse, in other words, you switch this, you put 1 on top. 1 was the smallest element here, another one will be the largest element. Of course, you get something else. For example, for natural numbers, you get 0, 1, 2, 3. Go on. If you reverse this, you will get the other part. You get something like -1, -1, -2, -3. You will get right. If you reverse this, you will get this one, isomorphic. This very least element. This will have a largest element. If you want, you can put 0 here, and 1 here, 2 here, and you say that the order is like this. The order is just reverse the order. Like you can say, in the subsets of X of A, subsets of A, X was this. Remember our ordering? Our ordering was B subset of C, right? Now you can replace this. You can say B, C, if and only if C is a subset of B. You can just reverse the order. You don't gain much doing this. Which one is the most important example? Well, they are all important to understand the concept, of course. But the most important one, the one that we use most, is this one. So you should understand this. For example, so let's do. Let's take Z and Z. Let's take X equal to Z and Y also equal to Z, both with natural orders. So I will make Y is here, 0, 1, -1, 1, 2, -1, and so on. This is Y. Z is equal to X and Y are equal. Remember, I need to make them disjoint. So I will take another copy, 0, 1, 2, -1, -2. But of course, if you give the same name, this will be confusing. So here, if you want to, you can put primes here, if you want to. If you don't want to, instead of this, you take 0, 1, 1, 1, instead of this. What they call it? Just erase this, 2, 1, 3, 1, and so on. -1, 1. And here, instead of this, you take 2, 0, 1, 0, 0, 0. So these are 2 copies. And here, the order is like this. It starts from -infinity, of course. These are smaller elements. These are larger elements. And then you order in between, among themselves here, you order them naturally. These elements are less than these elements. Here also, these elements are less than elements. And every element here is larger than this one. Okay. Now, let's talk about morphisms. Any questions about chapter section 1.1? Any problems about the definition? First year students can understand this course theoretically, but you need some maturity, some mathematical maturity that you may not have at this age, at this level of your education. But theoretically, first year students can understand these things. It's not too complicated. So, and partial order is something like this. It's something that, you order, salamak, you order them. X is less than or equal to X. If X is less than or equal to Y and Y is less than or equal to X, then X is equal to Y. If X less than or equal to Y and Y less than or equal to Z, then transitivity. And if you wanted total order, you want to be able to compare any two elements. Tamam mı? Ya tamam deyin ya tamam değil deyin.
Tamam
Tabii.
hocam. Tamam hocam.
Ya sağ dizi okulu mu orası? Bir şey yapmam. Zaten çok uzaktayız. Peki. Now homomorphisms. One point two. Morphisms. Morphisms of orderings. Let X less than or equal to and Y. You see, there's an ordering here. There will be an ordering here on X and also on Y. There's no harm in denoting both orderings the same way, although they may be different. Okay. If you have two different orderings on X, then you have to take two different symbols here. But if you have on two different sets, then you don't need to be two partially. It's called poset, partially ordered set. Let a map phi from X to Y is called a morphism. if x less than equal to x1 less than equal to x2, if and only if p of x1 is less than equal to p of x2. This if and only if is important. In some books, they only take this, but I will take this both. If for all x1, x2 in x, like this. In other words, phi preserves the ordering. We can also say that phi is increasing. For example, right? It doesn't reverse the orders. It keeps it. Example, take x to be ordering like this. This is x. This is larger than this. This is larger than this. But these two are not comparable. Take y here to be this only. This less than this. Now send phi. Take this one to send phi to this one. This is not A. Let's call this A, B, C, D, E. Send A and B to D's, to D, and C to E. Now this is a homomorphism. Is it true? No, it's not true. It's not true. Because it's not true. It's not a homomorphism. It looks like a homomorphism, but it's not. Because phi of A is less than equal to phi of B. Because they're equal. Phi of A and phi of B are equal. Right? Phi of A and phi of B are equal. So this is true. But A and B are not comparable. They're not comparable. This is not a homomorphism. If I had only this would be a homomorphism. If I define homomorphism, amorphism, it's the same thing, morphism or homomorphism, or endomorphism. If I define a morphism with only one-way implication, then this would be a morphism, yes. But if I do both ways, this will not be homomorphism. It's not true. But I give another example. Take natural numbers with the usual ordering both sides. Take phi, define phi to be x plus 1. Of course, this is increasing, right? So it's well ordering. This is a homomorphism. Or you can take x goes to p of x equal to 2x. This is also homomorphism. It's increasing. We will mainly speak about totally ordered sets. So we will not deal with sets like this. Yeah. We will deal only with totally ordered sets. So this is totally ordered, of course, but this is not because A and B are not comparable. A morphism between if let me see from a from a totally ordered set X into a partially ordered set Y must be one-to-one. Can you prove this? A morphism from a totally ordered set. Sorry, yes. From a totally ordered set into a partial ordered set Y must be one-to-one. Actually, oh yes, it's not true. Any morphism must be one-to-one. Morphisms must be one-to-one. So there is no way this can be a morphism. Morphisms must be one-to-one. Can you prove this? So you take a morphism from a well-ordered set X into a well-ordered set Y, phi, morphism, so it respects the order. So you have both implications. Can you prove to me that phi is one-to-one? I will wait.
Do you hear me, sir? Do you hear me?
I'm hearing you.
Should we show that if phi x1 equals phi x2, then x1 equals x2?
Exactly. Assume phi x1 equal to phi x2. Show x1 equal to x2. Okay, how do you do it?
X1 plus 1 equals x2 plus 1, then
What? Why should be plus one? I don't understand. So it's any morphism from there's no plus one here. X and Y are just any sets, any partial ordered sets. There's no plus one. Right? These are not numbers necessarily, x1, x2. They may be subsets. Of course, you have to use definitions, right? You have to use the definition of partial ordering, this, and definition of a morphism, this. There's nothing else you can use because it's about morphisms and partial ordered sets. Definition of partial ordered sets is here. Definition of morphism is here. So from these four statements, you have to show that phi must be one-to-one. I'm waiting. I'm sitting here. You have all the time to think about.
Hocam,
Efendim?
should we use the if and only if part of the definition of fee?
Hı hı. Tell me again.
The box you draw.
Yes. Yes.
Yes.
What about it?
If we
Yeah.
use that,
Of course you will use that. Of course. Because we are speaking about the morphism. So only one thing you know about morphism is this one. So you certainly have to use this.
Hocam,
Efendim?
x1 küçüktür x2 ve x1 büyüktür x2'yi göstermemiz gerekiyor ya eşit olması için.
Evet.
Tersini alma durumunu alsak, yani x1 bu kutunun içindeki ifadenin tersini alsak.
Hangi kutu?
Ancak
Bu.
ben
Ha?
tersini düşünemez miyiz yani?
Büyük değilse, küçük değilse, küçük değildir, o mu?
Aynen, küçük değilse büyüktür olması gerekiyor ya.
Hayır, olmaz. Bu tam sıralama değil ki bunlar.
Ha, bu da.
Değil mi? Tam sıralama olsaydı dediğin doğru olacaktı. Bundan dolayı. Küçük değilse büyüktür. Ama tam sıralama olmak zorunda değil. Benim derslerim normalde böyle geçer. Yani ben çok az ders veririm. Öğrencileri düşündürtürüm. O yüzden yani bu da öyle yapmamaya karar vermiştim ama şimdi emin değilim artık. Ee, yani çünkü haftada 2 saat dersimiz var. 2,5 saat. Ne? 2 saat galiba. 2 saat bile değil galiba. İyi kullanmam lazım zaman ama önemli değil. Önemli olan sizin öğrenmeniz. Dolayısıyla hoca sıkılıyor, işte çabuk yapalım falan diye şey yapmayın. Kendinizi stres altına sokmayın. Sakin sakin düşünün. Bunu biliyorsunuz. O1, O2, O3. Bir de bunu biliyorsunuz. Başka hiçbir şey bilmiyorsunuz. Buradan fi'nin birebir olduğunu kanıtlayacaksın. Yani fi x1, fi x2 eşitse o zaman x1'in x2 eşit olduğunu göstereceksin. Sen 4 tane önerme biliyorsun. 5.'sini göstereceksin. Benim tüm zamanım var.
Doctor, we can use the second one in the box or tree rule.
Again, tell me again.
There is a true rule, 1, 2, 3. Can we use second one?
Of course you
When-
can use. It's a free country.
Yes, like x less than or equal y. But here we can use it like x1.
Of course you can. Why not?
Okay, and then we will use it with the second box in the other board to show that x1 equal x2.
Well, what you want to put here x1, here x2?
Uh-huh.
Well, how do you know that x1 is less than or equal to x2? If x1 is less than or equal to x2, and if x2 is less than or equal to x1, then x1 is equal to x2, yes.
Yes,
But-
but the second board, it's already in the homomorphism rule. It shows like x1 is less than x2.
No, it doesn't say that x1 is less than or equal to x2. It says if x1 is less than or equal to x2, then phi of x1 is less than or equal to phi of x2. And if phi of x2 is less than or equal to phi of x2, then x1 is less than or equal to x2. This doesn't say that x1 is less than or equal to x2. When you say P implies Q, you are not
Okay.
saying that P is correct. You are saying if P is correct, if P is true, then Q is true.
So we can
Yes.
assume that it is x1, it is less than, and we can continue to prove.
No, you cannot assume anything. You can assume only things which are true. We are assuming this. We are assuming this. So we want to show that if phi of x1 is equal to phi of x2, then x1 is equal to x2. So you can assume this.
To get
This
this.
says P implies Q. Where is it? P implies Q. I was somewhere. Oh, I was it.
Oh,
P
yes.
implies Q means if P is true, then Q is true,
Mhm.
right? So you're assuming P, so you have to assume P and prove Q. Here also, if you want to show this statement, you assume this,
Two,
assume
yeah.
this, prove this,
Mhm.
okay?
Okay.
So you have to use this, of course. Without using this, you cannot prove that. Then you show that any x1 is equal to any x2, right?
Mhm.
Hocam bir şey sorabilir miyim acaba?
Tabii ki.
Biraz dersle ilgisiz olacak ama ben düzensiz öğrenciyim ve ilk dönem hiçbir dersi görmedim. Bu
Ne
dersi
öğrencisin?
öğrenirken düzensiz öğrenci. İlk dönem bir hazırlık okuyordum ve şimdi bölüme başladım. Ve bu dersi ilk defa görüyorum. Bir öneriniz var mıdır acaba öğrenim sürecimle ilgili? Sadece derse dinlemem yeterli olur mu?
Olur. Dersi hemen yeterli olur. I have to tell you that I have my notes. At notes in Turkish. www Nesin Köyleri org. There, at this page, at the bottom of the page, at the lower part of the page, you have something called e-kütüphane. There you have some books, some articles, some exercises, and so on about many subjects. And they are classified under algebra, geometry, trigonometry, whatever. And you look under matematiğin temelleri galiba. Matematiğin temelleri. Foundation of Mathematics. Temelleri. There I have two books. Not ready for publication, but almost. There are two books about axiomatic set theory. If I remember well, it's called axiomatic, Turkish, of course, unfortunately. Axiomatik kümelal kuramı. Kuramı bir, bu sayıların inşası. Construction of numbers. Sayıların inşası. The other book is axiomatic kümelal kuramı 2. It's about ordinal cardinals. So I'm going to treat this in this course, this book, as much as I can. I don't have to finish it because they're thick books. They're around 400 pages each. In the other course, in Tuesday's course, I'm taking this part. Here I'm constructing natural numbers. First, I give some axioms of set theory, and then I construct natural numbers, and then I will construct integers, rational numbers, real numbers. That's it. This is what I will do in this course. In this course, I will do ordinals, cardinals, well orderings, and so on. So here I assume natural numbers, for example. I assume everything we have done here. What about books in English? Well, these are good books. I believe these are good books because they try to make the subject, very deep subject, accessible to first-year students, for example. At Bilgi, I taught these subjects at the first year. Well, of course, subjects are difficult, so many of the students failed. But some succeeded.
Teşekkür ederim hocam.
Welcome. I believe I have to do it. Okay. So assume phi of x1 is equal to phi of x2. Then by O1, phi of x1 is less than or equal to phi of x2, right? And also, again by O1, phi of x2 is less than or equal to phi of x1, correct? What does O1 say? O1 says any element is less than or equal to itself, right? So if phi of x1 is equal to phi of x2, then phi of x1 is less than or equal to phi of x2, of course, because they're equal. And let's call this star. So I only did this part actually by star, then by star, we can take off the phis. X1 is less than or equal to x2, and also x2 is less than or equal to x1. So by O2, yes, by O2. You see, now x1 is less than or equal to x2. Now I can use it because I proved it. Before I didn't know it. X1 is less than or equal to x2, and x2 is less than or equal to x1. Therefore, x1 is equal to x2. So by O2, x1 is equal to x2. Six lines. 6 short lines. 4 sentences. 1, 2, 3, 4. Okay? Yes or no?
Yes, sir.
Yes, that's okay.
Wasn't it easy?
Yes. Yes.
It was easy, yes? Okay, so any morphism must be one-to-one. And if it's onto also, a morphism which is a bijection also, since it's a one-to-one, you only need to check its onto. Bijection is called an isomorphism. Let's call this phi between x and y. And x and y are called isomorphic. And we write x is isomorphic to y. You also say y are phi. If you want to. You can put phi here if you want to. What should you know about morphisms? One, composition of morphisms is a morphism. Take two morphisms, P and PC, right? You take a morphism, let's say phi from x to y, a morphism psi, say from y to z, between partial order, then you can construct psi composed with phi. You first apply phi, then you apply psi. Of course, if this respects the order, and this respects the order, in other words, if phi is increasing, and PC is increasing, then this is increasing also. Okay. 2, if phi from x to y is an isomorphism, so it's 1-to-1 and onto, then phi inverse from y to x is also an isomorphism. Of course, composition of isomorphism is isomorphism, of course. Composition of isomorphisms. Is an isomorphism. We can define automorphisms of a partial order set, x less than or equal to. These are the f's from x into x, isomorphisms from x into itself. This is a group of the composition. What do I mean? Maybe you don't know all. What do I mean? It means that first of all, let's say phi. If phi and pc are automorphisms, then phi composed pc is an automorphism. Close down the composition by is. And phi composed with pc composed with theta, say, is equal to phi composed with pc composed with theta, of course. And phi composed with identity on x is equal to identity composed with x with phi is equal to phi. And finally, phi inverse is also there. If phi is an automorphism, then phi inverse is also automorphism. This is what it means. This is clear by this. This is clear by this. The other ones are trivial. So it's a group. Exercise. Homework. Compute automorphisms of natural numbers with the usual order. Compute automorphisms of z with usual order. Compute automorphisms of n natural numbers with x divides y. With this one. X is less than or equal to y if and only if x divides y. This is one of the examples. Automorphisms of Q is much harder. Of real numbers also much harder. Okay, so compute these groups. What else can we do? Okay, compute automorphisms of this group. A number of elements. There's one element here, larger here, 2 by 2, like this. Only this first. Automorphism of this. Small ones are here, large ones are on top. And then take one more step, automorphisms of, this was 2 floors. Now let's have 3 floors. Let's call this T2. Let's call this T3. And in general, compute automorphisms of Tn. Number of elements, say, find number of elements. It may be difficult to find the group itself, but find its number of elements. Compute automorphisms of this. Larger elements are on top. They're smaller. These cannot be compared. We can find the group now. Find the group. Here, number of elements only, but here the group itself. Or you can take other automorphisms of. Yes. Well, next time. And you can start reading the books. This one, for example. Or maybe don't read the book. Maybe just try to understand the lecture and try to do the exercises and the homeworks. I will write my email. Nesin at I have Istinye address now, but I don't remember it. nesinkoyleri.org. You can send your homeworks here. Just give it, write it, subject, homework. So do it before next Wednesday. Okay? Any questions? Next time, try to speak more. Okay. Thank you very much.
Thank you, sir.
Thank you.
Thank you, sir.